One of the most important questions in all branches of engineering is how to evaluate the stability of an equilibrium point. In order to understand the concept of an equilibrium point, let us first consider an example of something that is not an equilibrium point. This is not an equilibrium point because the moment we allow time to move forward, the ball will roll down the ramp. On the other hand, this is an equilibrium point because as time moves forward, the ball will remain where it is. This is also an example of an equilibrium point, in that the helicopter will continue to stay at the same altitude. This is another example of an equilibrium point, but a very dangerous one. In theory, this ball should remain at the top of this hill. In reality, however, the moment there is even the slightest breeze, the ball will roll down the hill. We therefore call this an unstable equilibrium point. Now suppose that instead of a hill, we have a valley. The bottom of this valley is also an equilibrium point, but it's a very different type of equilibrium point than we saw before. In this case, if the ball deviates away from the center, it will always want to return to the equilibrium point. We therefore call this a stable equilibrium point. Whether an equilibrium point is stable or unstable is not always inherently obvious. In an actual helicopter, the altitude is controlled by adjusting the pitch of the blades. But for this particular example, let us assume that the pitch stays constant. Suppose that if this helicopter is above the desired altitude, the autopilot will turn off power to the engine driving the rotor, and if the helicopter is below the desired altitude, the autopilot will turn the power back on. The helicopter keeps overshooting and undershooting its desired altitude, and these oscillations keep growing with time. The desired altitude is an equilibrium point with this setup, but it ends up being an unstable equilibrium. At any moment in time, the state of a system can be represented with a vector. The vector does not need to be limited to 3 dimensions as is shown here. We can have as many dimensions as there are variables describing the system. The vector indicates the amount by which the state of the system has moved away from the equilibrium point. For example, If the rotor speed is faster than its equilibrium value, the amount by which it's faster is represented by the coordinate on this red axis. A negative coordinate on the red axis indicates that the rotor speed is slower than the equilibrium value needed to maintain a constant altitude. Most scenarios in real life fall in the category of what we call nonlinear systems. This particular nonlinear system has many different equilibrium points, some stable and some unstable. Even for the stable areas, the ball can escape if it deviates far enough away from the equilibrium point. Now, suppose the ball enters an unstable area. Even regions of instability can have small, stable areas inside them. If the ball does not deviate too far from this equilibrium point, this system will remain stable. As stated earlier, this is an example of what we call a nonlinear system. If the deviations from an equilibrium point are small, any nonlinear system can be approximated by a linear one. When we create a linear approximation, we are ignoring all parts of the system away from the equilibrium point. For the remainder of this video, we will assume that we have a linear system, or a linear approximation. An example of a linear system is a mass on an ideal spring. To predict the future behavior of the system, we need to know both the displacement and the velocity. These can be represented as shown with this blue vector. This blue vector is what we refer to as the state of the system. The rate at which the blue vector is changing can be represented with another vector. The white vector always points in the direction in which the blue vector is changing. Another way of saying this is that the white vector is the derivative of the blue vector with respect to time. Consider the state in which the velocity is the maximum at the beginning. Now consider the state where the displacement is the maximum at the beginning. Now consider both of these states together. Suppose we had a state at the beginning which simultaneously had both this displacement and this velocity. The fact that we have a linear system means that when the two blue vectors add together, the two white vectors will also add together. The sum of the two original systems at any moment in time is always the state of the new resultant system. Suppose we have a system in a state where the blue vector and the white vector are both pointing along the same line. Each time this is the case, the white vector is equal to the blue vector multiplied by a number. We call this number an eigenvalue of the system. In this example, both eigenvalues are positive real numbers. This means that for any state that the system can be in, the white arrow will always point away from the center. This means that the system will always move away from its equilibrium point. Positive real numbers for eigenvalues therefore represent unstable systems. Now let us consider a system where all the eigenvalues are negative real numbers. Here, for any state the system can be in, the white arrow will always tend to point towards the center. This means that the system will always move towards its equilibrium point, and the system is stable. But what about a system where some of the eigenvalues are negative and some of the eigenvalues are positive? States associated with the negative eigenvalues will move towards the equilibrium point. And states associated with the positive eigenvalues will move away from the equilibrium point. If the system contains even a single positive eigenvalue, the system as a whole is unstable. The eigenvalues do not need to be confined to just real numbers. Here is a system where the same blue vector has two different eigenvalues, both of which are imaginary. This eigenvalue will cause the blue vector to rotate as shown. This other eigenvalue will cause the blue vector to rotate in the other direction. The actual system is the sum of these two blue vectors. The sum is always a real number. This is always the case, since any parameter that this variable represents must always have a real value. What is shown here is just one of the variables of a system, and this variable keeps oscillating. Purely imaginary eigenvalues represent systems like the ideal spring we saw earlier. But what if our system has an eigenvalue with both a real and an imaginary component? Here is a system where the same blue vector has two different eigenvalues, both of which are complex numbers. The real components of both eigenvalues are positive. Each blue vector rotates and grows in magnitude. The actual system is the sum of the two blue vectors. The sum is a real number which keeps oscillating. But unlike in the previous example, the magnitude of these oscillations keep growing with time. Systems with complex eigenvalues where the real components are positive represent examples like our unstable helicopter. Here, the magnitude of the oscillations keep getting bigger. But what about a system where the oscillations keep getting smaller? If the oscillations keep getting smaller, the eigenvalues must have a special property. In these cases, the real components of the eigenvalues are negative. As before, the actual system is the sum of these two blue vectors. This represents one of the variables in an oscillating system where the magnitude of the oscillations keeps getting smaller. If the oscillations keep getting smaller, then this represents a stable system. For a system to be stable, the real components of all the eigenvalues have to be negative.